Hello, my name is Kevin Craig. This presentation is an introduction to the Mechatronics Studio at Hofstra University, which is located in Adams Hall, room 113. This studio is open to students in classes in the Mechatronics Studio 24 hours a day, 7 days a week. The two main classes that are taught in the Mechatronics Studio are modeling, analysis, and control of dynamic systems, and mechatronics. There are several maxims that are appropriate for the courses that are taught in the Mechatronics Studio. Festina lente is Latin for make haste slowly. The expression slow is smooth and smooth is fast comes from the military, in particular the Navy SEALs. Predict before you measure. One does not make any measurements unless they've done the appropriate modeling, analysis, and prediction so that when you do measure, you know if the measurement is correct or just garbage. And lastly, in working in the Mechatronics Studio, always think about what you are doing and why you are doing it before you do it. What is mechatronics? Mechatronics is multidisciplinary systems engineering. This diagram, which I created in 1995 when I was a professor at Rensselaer Polytechnic Institute, shows that mechatronics is the integration of mechanical systems, electronic systems, computer control, and computers, all integrated in the design process from the very start of the design process. Mechatronics is technology integration to achieve optimal system functionality. What is a studio? Well, it's not a lecture and it's not a lab. It's a studio. And in a studio, you hear, see, and do in many forms. You've heard the expressions, when I hear, I forget, I see and I remember, I do and I understand. Repetition and practice leads to confidence. In the Mechatronics Studio, the capacity is 20 students, and the 20 students work in two-person teams at the 10 stations in the Mechatronics Studio. What happens in the Mechatronics Studio? Well, there's lecture and discussion, problem solving, computer simulations, hands-on hardware activities, student-instructor interaction, student-student interaction, team-team interaction, and it's open 24/7, and so there are many after-hours informal discussions. Here you see the equipment in the drawer of a Mechatronics Studio station. We have a multimeter, cables, and probes. This is the National Instruments MyRIO. RIO stands for Reconfigurable Input-Output. The National Instruments MyDAC, which is a data acquisition device. This is another National Instruments data acquisition device. Here are two brushed DC motors with magnetic tachometers, the Arduino Uno microcontroller, the breadboard on which we build our electronic systems, and here are several probes that we use with our oscilloscope. Here you see the equipment that is used in almost everything we do in the Mechatronics Studio. We have a waveform generator, we have an oscilloscope, and we have a multimeter. For almost every exercise that we perform in the Mechatronics Studio, there is a BNC cable from the output of the waveform generator to channel 1 of the oscilloscope. As you can see, channel 1 is from the waveform generator. The other cable, which is connected to this T on the waveform generator, goes from the waveform generator to the system under test. That cable has mini grabbers on the end of it. And then the oscilloscope in channel 2 has a cable with mini grabbers on the end that is an oscilloscope probe. So channel 2 comes from the system under test. And this is our digital multimeter, which performs a variety of functions. These are the two oscilloscope probes we use. The BNC cable, which goes from the waveform generator to channel 1 on the oscilloscope, and the probe, which is designed for the oscilloscope, is a passive probe with an amplification of 10, and this goes from channel 2 on the oscilloscope to the device under test. Here is our digital multimeter, and we'll talk about the variety of functions it has in a minute. And this is the DC power supply that we use for all of our testing. The DC power supply has a 5-volt fixed output with a limit of 3 amps, and then it has an adjustable plus or minus 15-volt output with a maximum current of 1 amp. And the adjustment here is very coarse, and it goes from a little bit more than 0 volts to a little bit more than 15 volts. So we nominally say plus or minus 15 volts. Here are the 5 connectors that we use for connecting the power supply to our breadboard. This is the ground for the plus or minus 15 volt side of the power supply. This is the plus 15 volt output, the minus 15 volt output. This is the fixed 5 volt output, and this is the ground for the fixed 5 volt output. The ground of the 5 volt output and the ground for the plus or minus 15 volt output are not the same. So if you will be using both of these voltages, you need to connect these two grounds together so we have a common ground for our system under test. Here is our digital multimeter, and you can see all the measurements that it performs: AC and DC voltage, resistance, continuity, diode, logic, frequency, duty cycle, capacitance, inductance, AC and DC current. You need to be familiar with the breadboard you'll be using for your electronic systems. The multimeter can check for continuity. Here is a portion of a breadboard. You can see the green lines indicate where the holes in the breadboard are connected together, where we have continuity. So here we have continuity, and here, and here, 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 here. So in the rows in each of these sections of the breadboard, we have continuity. In the portion of the breadboard where you have 2 columns of holes, there is continuity in each column, along the entire column, but not from one column to the other. And similarly, on the breadboard, there are divides, sort of a trench, and there is no continuity across that trench. So a row on one side of the trench is not connected to a row on the other side of the trench in the breadboard. To filter out high-frequency noise from the DC power supply, we placed 2 capacitors in parallel. One is a ceramic capacitor, typically 0.01 microfarads, which is not polarized, and an electrolytic capacitor, which is typically 1.0 microfarads and is polarized. The plus lead is the higher voltage, the minus lead is the lower voltage. We use both of these on the DC power rails, and we combine them in parallel. The reason we use an electrolytic capacitor and a ceramic capacitor in parallel is as follows. The large capacitor is an electrolytic capacitor with high capacitance and low cost, typically 10 microfarads. The terminals have polarity and cannot be inverted, otherwise the capacitor can explode. The electrolytic capacitor consists of two metallic foils that form the capacitor plates wrapped with an insulator between them. Although this type of capacitor can reach high capacitance, it also has high unwanted parasitic inductance. We will learn about the effects of parasitic inductance and parasitic resistance on a capacitor in later sessions. The small capacitor is a ceramic capacitor. The capacitance is low, nominally 0.01 microfarads. The terminals do not have polarity. The rated voltage of this type of capacitor is in general higher than electrolytic capacitors. A major advantage of this type of capacitor is that the parasitic inductance is low. We also use a device which comes from National Instruments, and it's called the MIDAC. DAC stands for data acquisition. Here you can see some of the specifications, the analog inputs and outputs, the digital I/O lines, the power supply, the audio input and output, and others. Why do we use the MIDAC? The MIDAC gives us access to an assortment of virtual instruments. These virtual instruments are shown here, and there are many, and they can replace the hardware instruments we have in the Mechatronics Studio. For example, there's a virtual oscilloscope, which could replace our hardware oscilloscope. There's a virtual arbitrary waveform generator, which also could replace our actual hardware waveform generator. But of all of these, the most important virtual instrument we use is called the Bode analyzer for frequency response measurements, which is the gold standard for experimentally determining the model of any dynamic system. The Bode analyzer is simple to use and very fast in obtaining results. And the hardware version of a Bode analyzer is called a dynamic signal analyzer. And in fact, there's a dynamic signal analyzer here available as a virtual instrument. Its price tag is in excess of $20,000. So we'll be making use primarily of the Bode analyzer and maybe one or two other virtual instruments in our work in the Mechatronics Studio. Most importantly, here are the Mechatronics Studio guidelines that must be followed by each and every student in any course they take in the Mechatronics Studio. The first is, upon entering, you will swipe your ID card and also swipe your ID card when leaving. And this applies to regular class time and also to anytime you come to the studio outside of class time, since the studio is open 24 hours a day, 7 days a week. Once you enter the studio, wipe down the station with the antiseptic wipes that are available at the entrance. You will place all book bags under the station, not in the aisle where people can trip over them. You will check the contents in your station drawer. In your drawer, you should find 5 banana cables, and they're called that because of the end of the cable. Looks like a banana. And there are 2 red, 1 green, and 2 black. There is one BNC cable. The BNC refers to the end of the cable. There's a BNC mini grabber cable. And then there's the gray oscilloscope probe, meant to be used with the oscilloscope, and it has a BNC on one end and a mini grabber on the other. You will remove the component box for the exercise to be performed from the station drawer. You will have a box with components with each exercise labeled on the appropriate box. And you will make sure not to mix up components between boxes. And of course, components need to be returned to the box when you're done. And this applies during class time and also in outside of class time. You'll then remove the breadboard with the noise suppression capacitors mounted from the station drawer. The noise suppression capacitors should never be removed and just left in place. You'll remove the multimeter with attached probes from the station drawer, as you will almost always need to use that. Then you can remove the NI-MIDAC or NI-MyRio from the station drawer if needed. You will then perform the studio exercise on your own time in the Mechatronics Studio. We will not be performing electronics exercises, studio exercises during class time. We may perform parts of some studio exercises, but performing the entire studio exercise is your responsibility to do on your own time in the Mechatronics Studio, since the Mechatronics Studio is open 24 hours a day, 7 days a week, and you need to commit 6 hours of outside class time to any course that you take in the Mechatronics Studio. You'll place the components back in the box and put the box in the drawer along with the breadboard in its initial state when you're done, along with the MIDAC, MyRio, multimeter, and cables. You will then check the area, table, and rug for any trash. Leave the station as you found it. Wipe down the station with the antiseptic wipes if needed. And when you leave, swipe your ID card. This is the introductory exercise, which you will perform on your own time during week 1 of the course, Modeling, Analysis, and Control of Dynamic Systems, and you'll perform this in the Mechatronics Studio. The first part of the exercise deals with multimeter basic measurements. In this part, you will check the breadboard continuity. You will set the DC power supply voltages and measure them, both the plus or minus 15 volts, which is variable, and the fixed 5 volt output. You'll measure the resistance of a resistor, compare the color code of the resistor to what you measure, and note the tolerance. You'll use a potentiometer and see how it can be used as a variable resistor, but also a voltage divider. You'll measure the capacitance of the 3 types of capacitors: ceramic, electrolytic, and tantalum. The tantalum and electrolytic are polarized. The ceramic is not. You'll measure the inductance of an inductor. You'll check the operation of a diode. Check the operation of a power transistor, the MOSFET, metal oxide semiconductor field effect transistor. And you'll take a 741 op amp and you'll place it in a buffer configuration and verify its operation where the input equals the output. I have created a GoPro video of me performing all of these activities so you can have guidance as you go through them on your own in the Mechatronics Studio. The second part of the introductory exercise deals with oscilloscope, waveform generator, basic exercises. In this second part, you'll choose a 10 hertz, 2 volt peak to peak sine wave with a 3 volt offset, and you'll send it from the waveform generator to channel 1 of the oscilloscope. On the oscilloscope, you'll display 5 cycles of the input signal and verify that the frequency, amplitude, and offset of the sine wave are correct. And you'll use cursors and measurement keys to perform that verification. Before you actually turn on the channel of the oscilloscope, you want to set the scope voltage and time scales that correspond to the waveform that you're measuring. And you do this before you turn on the output of the waveform generator or turn on the channel 1 of the oscilloscope. The reason you do this is to show that you know how to predict what you should observe on the oscilloscope and not simply turn on the oscilloscope, observe garbage, and then start playing with the knobs, hoping to get the signal that corresponds to what you set in the waveform generator. Doing this will show everyone around observing you that you are expert in the use of this equipment and have great confidence. Similarly, you'll choose a 10 hertz 2-volt peak-to-peak square wave with a 1-volt offset and send it to channel 1 of the oscilloscope. And similarly, you'll display 5 cycles of the input signal on the oscilloscope, verify the frequency, amplitude, and offset of the square wave, use cursors as well as measurement keys, and again, you'll set the scope voltage and time scales before inputting the signal. Again, to show the people observing you that you are expert in the use of this equipment and you have confidence in the use of this equipment. Of course, this will take time to become expert, and the more you practice, the more expert you will become, and the more confidence you will have in this equipment, which is used by mechatronics engineers worldwide in all of their activities. Thank you for your attention. I wish you great success in performing this introductory exercise. With practice and repetition, you will gain confidence, and in the process, you'll have a great deal of fun on the journey to become the engineer that you want to become.